So where we want to begin is at the beginning with what are we measuring? What are we interested in? So our life is pretty much comprised of things that are constant and things that vary. So luckily, the sun comes up every morning. You know, that's a constant. As long as we're still alive, we wake up every morning. That's a constant. Now, outside of some of those constants, we're always hungry. You know, we're human beings. We have these drives to procreate and, succeed, to live, and that kind of thing. Those are constants. But outside of that, we have variables, and these are just far-ranging. Anything that changes, anything that varies. It's hard to underestimate how many things in our lives are variable. So we wake up, maybe we're hungry for some, usually we eat oatmeal, but one day we're hungry for, fruit and yogurt. So what we're hungry for is a variable. Driving to work, how fast we get to work, that's a variable. The gas mileage we get in our car on the way to work is a variable. The temperature, is it sunny or not? All of these things are varying. So our life is really composed of variables. So it should be easy to find variables of interest to you. Now, in the research setting, variables are defined much more specifically, and that's what we talk about with like construct validity. So we have to be able to say what a variable is and how do we know we're measuring what we want to be with that variable. So a constant is something that never changes. You could represent a constant with a single number because it's never going to change. It could always be a 0. It could always be a 1. It doesn't really matter. Gravity is a constant, and gravity has a single equation that's used, no matter what. So that's a constant. But variables, they have to have different levels because just talking about is it sunny or cloudy, that's 2 levels. So sunny could be measured or represented by the number 1, and cloudy could be represented by the number 2. So a definition or a characteristic of a variable is that it varies and it has more than one level of measurement. So it has to have 2 or more levels. The number of levels it has isn't indicative of how interesting it is as a variable, how important it is. It just has to have variation. It's in the name, variables. So, like I said, this is part of our everyday life. We are surrounded by variables, and what we do is we try to make sense of variation in our lives. Whether we do that with intuition, whether we do that with experimental methods, research methods, we do it a lot of different ways. Now, variables have to, especially in the context of research methods, need to be able to be defined. So how do we know what we're actually measuring? So we come across this idea of how a variable is operationalized, or the term operationalization. This is what we do to measure something. So and an operationalization is not, there's not one operationalization for any given thing. So something as simple as distance, it can be operationalized in different ways and measured in different ways, whether it's inches, meters, those different kinds of things. The underlying concept is there. It's how far things are apart. But the way that we measure that can be different. So we have different operationalizations of length. That's a very easy concept to understand. But when we talk about something like depression, how do we operationalize the concept of depression? There's a lot of ways to go about it. One way, that's pretty common is just to ask the person, in the last 30 days, how many days were you feeling sad, blue, moody? All of these terms we use to represent depression, and then the person will respond. And then we have a self-reported measure of depression. So that's one way to operationalize depression. Another way is to use a battery of items. So we ask this person 20 to 30 different questions that measure different components of depression. So, maybe anxiety, sleeplessness, loss of appetite. What would be some other ones? I don't know. What would be other indicators of depression? Yeah, sleeping too much, so changes in sleeping patterns. Yeah, loss of interest in activities that you're usually used to and that kind of thing. Those could be good indicators. And then what we could do is either add all of those up. So we have an additive scale that from maybe 0 to 50, people that are 50 are the most depressed, people that are 0 have no depression, and most people fall somewhere in between. That would be a good operationalization of depression that takes into account multiple variables. So it doesn't matter how many times or how many ways a variable is operationalized, but that operationalization has to be good. It has to have validity. So before I move on to the next, so a variable must have an operational definition to be studied. So you have to be able to tell somebody how you're measuring something before you can go on and measure it. Or else everybody or anybody could think of, so let's just say I'm studying depression. I found that people were more depressed that had to come to summer school than people that don't. Well, how did you measure depression? Was it self-report? Was it something that they used a scale? Did you actually use maybe physiological responses or something? So we have to be able to communicate to others how we measure a variable, and that's why we operationalize, is we can recreate the measurement. Somebody else can measure that variable the same way. So it's really important to be able to define how you measure something. Construct validity is how good we operationalize something. So this is where that depression example, this could vary. So when we ask somebody how depressed they are, they give us their response, and how much, so what was that person thinking about when they responded? Was it, maybe kind of saving face and saying, oh, I'm not depressed, because depression is kind of stigmatized in our society. It only captures that person's self-report of depression, where if we talk and survey them on all of these different concepts, so sleeplessness, loss of interest, all of these different things, then we probably get a better overall measurement of depression, because we're not just asking that person, oh, do you feel yourself to be depressed? But we're judging that person on all of these multiple indicators that we know from scientific study represent depression. So that's something that I talked about a lot, or we talked about a lot in my structural equation modeling course, and a good way to think about operationalization and construct validity is the more things you can ask about the same topic, the same variable, usually the higher construct validity you have. So imagine that this is a one indicator measure of depression, and it's just the self-report. So this is the variable itself, and this arrow represents measurement error, which we'll talk about. So no matter what we're trying to measure, usually there's some error in our construct or our operationalization. There's individual variability. So we have a one indicator measure of depression. But what if I, like I said, use multiple indicators? And you can imagine we have 15, 20 indicators of depression. So what happens is that the error in our measurement is reduced because we're adding together all of these different things that measure the same concept. So this pretty much represents this directly. So anytime this varies by 1 unit, this will vary by 1 unit. So I could really just, hide this, because there doesn't really need to be another indicator. We just have a self-report variable. Where here, this is actually a latent variable that's measured by a bunch of different things. So it's not just when this varies once, and if you screwed up the measurement of this, this is automatically screwed up. But you have a variety of different measures that are kind of the effect on depression, or the representation of depression is kind of an average of how all of those vary together. So you get a better operational definition of depression because you're measuring it all these different ways, and you're getting at, you're kind of looking at it from the front, from the back, from the side, all of these different ways. So you're kind of triangulating how you're measuring this. So that's really important in creating a variable with higher construct validity. That's a pretty advanced description of it. It could be as simple as, the scale that you weigh yourself on in the morning. How valid is that as a measurement of your weight? So if your scale measures you in something that's not directly related to weight, maybe it's not a good way to weigh yourself. Sounds redundant. But so, like, there's a lot of scales have body fat mass, like indicators. So you stand on them and they put like electric through your body and they give you a measure of body mass. So how accurate can that really be? And a lot of you in nutrition probably know that like BMI is really not a good indicator of body mass. And that sort of simple, like electronic going through your, like electrode, like impedance is what it uses to say how much fat you have in your cells, is really not a good indicator of your actual body fat percentage. It needs to be measured in, I think they do, like where you go in water and it looks at how much water is displaced, and they measure your bone mass and muscle mass and then figure out your body fat content. So the construct itself, I think, well, I guess this is kind of, I don't know how I'm going to get at it. Body fat itself is a variable, and it's measured in different ways. So when you measure it using this impedance through a cheap home scale, you're not going to have as much validity in your measurement of that variable as when you use more advanced, precise ways of measuring it. So we always want to use precise ways of measuring things, and that kind of goes back to how we measure depression. Is it's much more precise to ask all of these indicators of depression rather than just ask one question: are you depressed? So now that we've talked about how to measure single variables, what we really are interested in and will focus on throughout the most of the semester is looking at relationships between variables. So instead of just saying this is how we measure one variable, we really need to do that for at least two variables and look at the relationship between the two, because we want to see what is associated with increase in other variables, what's associated with decrease in other variables. Are there differences in the average of a variable across groups? So a lot of different ways to look at relationships. But what we'll focus on now is looking at correlation and looking at the relationship between two continuous variables, or two variables that should ideally be measured at the interval or ratio scales that we've discussed. So this is not in the book, this figure here, but I want to make sure we all understand how to look at a graph and be able to understand why it's set up the way it is usually. So at some of the figures we're going to look at in a few slides, what we're going to look at is a figure like this, where we have an x and y axis. The x-axis is always on the horizontal plane. This is usually the variable that we identify as the independent variable or the explanatory variable. So considering the relationship between two variables, we usually have one explanatory variable and one response variable. So we have one variable that predicts the other variable. So on the x-axis, that's where we usually put the variable that we believe explains variation in the dependent variable, or the variable we plot on the y-axis. So the y-axis is always on the vertical plane. What we'll talk about later in the semester is regression, and if you're familiar with algebra at all, you might remember the regression equation, which was y equals mx plus b, or y equals a plus b of x. Y is really kind of the same thing here on the y-axis. So y is our predicted value in a regression equation. So what we have on our y-axis is our predicted value of the outcome, or the response variable. So that's what we see here. Another thing that's important is the origin on both of these axes. So as we set them up, and usually if you're setting up a scatter plot, which is displayed using this kind of graph, you usually want the origin point to be 0 on both axes, so you can actually get a true depiction of the complete range of the variables. Now, this doesn't happen a lot of the time, especially if we're talking about maybe years of education on the x-axis predicting income on the y-axis. You can imagine that there's a lot more space between 0 and your average income on the y-axis than there is on the x-axis between 0 and highest years of education. So sometimes you need to rescale the axes to fit the different variables that you're looking at. But it's always a good practice to try to use 0 as the origin point for both of these. So now that we understand kind of the map that we are going to draw these relationships on, we can look at the different kinds of relationships between two variables that are measured at the interval or ratio scale. So one that fits well with our example of the relationship between education and income is a positive linear relationship. So in a positive linear relationship, as one variable increases, the other variable also increases. So if we have education as our explanatory variable on the x-axis, and we have income as the response variable on the y-axis, as each year of education increases, we should also see an increase in income if there is a positive linear relationship between these. So that's just one example. There's almost infinite examples that you could use to understand and I guess typify a positive linear relationship. Now a negative linear relationship is just the opposite. So as your explanatory variable increases, the other variable, the response variable, should decrease. So this could be, maybe let's talk about years of education again as the explanatory variable, and maybe depression as the response variable. So if we have the assumption that as education increases, the levels of depression in individuals would decrease, that could be a negative linear relationship. So for each unit increase in education, we have a given level unit decrease in depression. Now, positive and negative linear relationships can only focus on linear relationships, so there's no curve in it at all. And what this is a somewhat abstract way of thinking about relationships, because usually there are points at which the relationship is not as strong. Maybe even the direction of the relationship decreases. So in the first half of the relationship, we have a positive linear relationship. And then in the second half, so the higher levels of our x-axis, we have a negative linear relationship. So this is what's defined as a curvilinear relationship. So in a curvilinear relationship, increase in one variable results in systematic increase, then eventual decrease in another. So a curvilinear relationship can be U-shaped. It could be like an inverted U-shape, maybe like a horseshoe that you would think about. And that's also kind of the ideal type of a curvilinear relationship. For the most part, what you'll get are kind of weak arcs, weak trajectories that have change that's nonlinear. As long as it's not linear, we would define that as a curvilinear relationship. Finally, the other type of relationship that may exist between two continuous variables is pretty much no relationship. So what we would see is a flat line. As x increases, there's no change in the y variable. So this is what a scatter plot would look like with a regression line. If there's no relationship between the variables, pretty much that line of best fit would really just follow the horizontal axis. Now, we've talked a little bit about the different kinds of relationships there are between variables, and the next slide will actually look at those a little bit more. But what we want to talk about now is how we can actually quantify the relationship between two variables. So we want to be able to give a numerical value to the relationship between two variables. So we've talked about positive linear relationships and we've talked about negative linear relationships. So that gives us some idea that maybe we want a value that has positive values indicative of a positive linear relationship and negative values indicative of a negative linear relationship. So what we can use to calculate and quantify the strength of the relationship between two variables is a correlation coefficient. So I'm sure you've heard of correlation before, but a correlation coefficient is a specific statistical value that we calculate. And what it is a numerical index of the strength of relationship between variables. So a correlation coefficient, and we'll talk about it more in the semester, is between the values of -1 and +1. So you could imagine that if there's no relationship between two variables, we would have a correlation coefficient of 0. If we have a perfect positive linear relationship, we're going to have a correlation of +1. And if we have a perfect negative linear relationship, we're going to have a correlation coefficient of -1. The distance away from 0 in the correlation coefficient, that indicates how strong the relationship is. So at 0, there's no relationship, but at the extreme ends of +1 and -1, those are very strong relationships. So that's something that's important to remember. Also, something that's really important is that a correlation coefficient can only give you an indication of the strength of the relationship if the relationship is linear. It is not designed to measure curvilinear relationships. So you'll get a term that is biased and has a lot of error in it if you're trying to calculate a correlation coefficient for a curvilinear kind of relationship. So before we look at the figures, it's important to understand why we want to look at the relationship between variables. So looking at the relationships between variables and identifying relationships helps us reduce uncertainty in our lives. So we can just imagine, if I'm trying to figure out how I can have more energy during the day, and I was brought up never eating breakfast, so I never had breakfast, and I've always kind of, especially in the afternoon, gotten kind of tired and that kind of thing. So I'm trying to figure out ways to reduce my tiredness later in the day. So what I do is I start having, a cup of Greek yogurt every morning. And what do I find? Maybe I find that my energy is better later in the afternoon because I've had something that has some good fat and good protein in it to start. So what I'm starting to see is a relationship between what I eat for breakfast or eating breakfast and how I feel the rest of the day. So where previously I may have been uncertain as to what was causing my tiredness at the end of the day, what I can start to see is that maybe it's actually a product of what I eat for breakfast, and that helps me reduce uncertainty in my life. So I want to get rid of the tiredness, so what I need to do is start eating breakfast. So it really helps us to kind of get a sense of how the world works and the relationships between things. So identifying relationships is very important for us in research methods because that's really what we're doing. Of course, we need to be able to describe individual variables themselves. So we'll talk about an average later and a standard deviation and the distribution of a variable. But really what's more interesting to us as social scientists are the relationship between variables. So like I've used this term ideal types, which identifies to me sort of the theoretical concept that we're talking about. So a positive linear relationship, a perfect positive linear relationship is almost a theoretical concept because in practice, it usually never exists. We never usually find a relationship between two variables that is a perfect positive relationship that would be a correlation coefficient of +1. We usually don't see that. Usually in practice, we have not strong relationships between variables. Usually there's curvilinear relationships. So while we've learned these concepts in kind of a vacuum, in a lab almost, in actual practice in everyday life, we need to be more flexible, because what we're going to see are relationships that really aren't identified by a perfect positive linear or perfect negative linear relationship. Now, looking at different figures of, we could call correlations, or we could call types of relationships between variables, is what we have here. Graph A shows us a perfect positive linear relationship. And what we have is a explanatory variable of speech rate, and then we have the response variable, the Y variable, attitude change. So what we see is as speech rate increases, attitude change also increases, and this is a perfect positive linear relationship. So if we had a linear relationship that wasn't perfectly positive, we would probably have a line here, the blue line that's on the diagonal. It just wouldn't be as steep. Instead of being a 45-degree angle, it might be a 30-degree angle, a 25-degree angle, that kind of thing. Same holds for a negative linear relationship shown in graph B. Here we see that as group size increases, the amount of noise decreases. So the larger a group gets, the lower the amount of noise made by that group. So for whatever reason, small groups are really noisy, large groups aren't as noisy, is what this indicates. So this is a negative linear relationship, because for each unit increase in the size of the group, there is a given number of unit decrease in the amount of noise. Graph C shows us a curvilinear relationship. Again, this is a theoretical ideal type, because even in curvilinear relationships, usually they don't look clean like this. Like I said, there's some sort of variation on an arc. It doesn't look like a horseshoe or an upside down U. What this shows us in graph C is, as the complexity of a visual stimulus increases, liking for the stimulus doesn't increase over the complete amount of change and complexity of visual stimulus. What we see is that people like a stimulus that has about a medium level of complexity for that visual stimulus. As the complexity of visual stimulus gets extremely high, we dislike that. The respondents that this data comes from shows that at high levels of the complexity of visual stimulus, we don't like that stimulus as much, and that's the same for low levels of complexity of a visual stimulus. So that makes sense. So anything that's either too boring or too busy, we're really not that into, but we actually like a stimulus that has a medium amount of complexity. So you could think about this as maybe in a movie or something, a movie that has very, very basic, very dry, very boring visual stimuli. We probably don't like that as much as something that has a medium amount of stimulation, amount of change, amount of effect, and that kind of thing. And also these movies that just have tons of special effects and things are changing every 2 minutes, and maybe horror movies where everything's kind of the first person videotape taking. I don't really like those personally, but maybe you do. But that kind of high complexity of visual stimulus is hard for me, and that's kind of what this graph shows. So curvilinear relationships, they're able to describe more complex relationships. So not just as one increases, the other increases, but there's some amount of increase and some amount of decrease given the different levels of the variables. Finally, graph D shows us a pretty much no relationship. So as the amount of crowding in a classroom increases, performance level doesn't change here. So our explanatory variable is amount of crowding, our response variable is performance level, and what we see is that as amount of crowding increases, the performance level does not change at all, and that shows us that there's no relationship between those variables. So we've talked about relationships between variables. We're to the point now of maybe we want to manipulate that x value to see how y is influenced. So maybe we want to actually, instead of just randomly eating a given amount of food every day, we want to say, okay, today I'm going to wake up and have yogurt and almond butter. That's one of my favorite breakfasts. I eat that almost every day, and I feel good. So, but say I'm ready to make a change, and I feel like maybe I'm getting bogged down. There's too much protein or something in it. So I'm going to start eating something else. So I'm going to make a change and vary the type of food I'm eating for breakfast, and then see how I'm feeling at noon. And maybe I really want to see if there's a perceptible difference in my mood and energy halfway through the day. So every day over the next 2 weeks, I'll just kind of check in with myself and say, oh, how am I feeling around noon? And see if eating another kind of breakfast, maybe oatmeal in the morning, changes that. So now I'm starting to manipulate variation. Now, there's basically 2 ways of doing this, and the rest of the course is dealing with these 2 different ways of manipulating variables. First, we have the non-experimental method. So this is where we pretty much make observations of what's already going on and then calculate the relationships between things. So variables observed as they naturally occur. So this depression thing, we go and we do a random survey of everybody on campus and ask them 30 different questions about depression. Then we ask them about how much exercise they do. It's not experimental. We don't have controls in place because what's making, maybe what's different from everybody on campus today than everybody that's on campus in the fall. So maybe everybody that's summer school attendees are less depressed just by nature. Maybe they exercise more just because that's the type of person that comes to summer school. We can't, if we don't measure people that come to the fall, spring semesters and measure the same variables, we don't know if that, attendance in summer school versus attendance in the normal semester schedule has a impact on the relationship between exercise and depression. So that's that time of the year you're coming to school becomes an extraneous variable. We call that a third variable. When an extraneous variable is identifiable and you can name what it is, we call it a confounding variable. So this is a variable that exists outside of the relationship between your 2 focal independent and dependent variables. So this can be anything, and there's tons of them. So you can imagine the relationship between exercise and depression. What can you guys tell me, like extraneous variables that would exist in that other than maybe semester of student? And start from the most basic. Gender. It's a good one. Age. Anybody else?
Maybe like past athletic experience.
Right. So training.
Used to be an athlete. Type of exercise.
Type of exercise, right? So 30 minutes of walking versus 30 minutes of lifting or something.
Time, hours.
Yeah. So how much they commute, right? So no matter how much exercise you do, if you commute 4 hours a day, you're probably depressed. So there's a lot of extraneous variables, and they're ranging in, just like we've started, and ranging from these scripted characteristics of individuals, so gender, race and ethnicity, age, to things in people's everyday lives, how long they have to commute to work, what kind of exercise they're doing. Do they have family predisposition towards depression and that kind of thing? So extraneous variables are everywhere. So if we're using non-experimental methods, how do we control for these? So if we're really interested in the relationship between exercise and depression, it's really hard in non-experimental methods to rule out all of these confounding variables. So it's very difficult. Now, I say that, but this is the kind of research I do. I've never randomized two groups, put one into an experimental treatment and one into a control condition. I've never done that. The statistics that we have today can help us control for confounding variables. So if I did a survey of students here on exercise and depression, and let's say that I do measure people in summer school and I do measure people in the fall, what I can do in pretty much this equation is add a slope for time of year, I guess. Summer school versus normal. I don't want to say you guys are non-normal for being here at summer school, but traditional semester, I guess I would say. And then what that would do is I would have a measurement of how much variation in the outcome variable is related to type of school or schooling. And then what that would do is pretty much subtract that variation out of my predicted outcome. So what I'm left with is a truer relationship between exercise and depression because I've taken out the variation for time of year you're going to school. That can get much more complex, and I just want to say that because definitely experimental methods are the golden standard of research methods, but a lot of people don't use them. So don't feel that if you're not interested in the experimental stuff and you haven't been taught experimental methods, you've never used them, don't feel bad about it. Maybe I'm just getting this off my chest because I feel bad about it. I don't know. Maybe that's something you could measure. So the experimental method is, like I said, this is the gold standard of identifying relationships between variables. And the reason is because you can control, you can pretty much take out of the equation all confounding variables. Now, there's multiple ways to do this. So, two ways really, experimental control and randomization. So in experiments, and I know you've been exposed to this somewhere, is that an experiment has at the very least, one group that receives the experimental value or whatever the actual, I guess, device is or the cause that you're perceiving to or you're hypothesizing to affect the outcome. So I always talk about just like studies of drugs in this example. It's really easy to think about. So I'm doing a study of blood pressure. How does my blood pressure medicine work? So I'm GlaxoSmithKline, and I came up with this new blood pressure medicine that I think is really good. How am I going to prove to the FDA that it is valuable, that it's actually reducing people's blood pressure? So what I would do I would start, actually this would be the second part. First I would randomize individuals. So I would get as many people as I can afford, but let's say we have 10,000 people total. We randomly select 10,000 people from the population and they agree to be part of our blood pressure study. So I have these 10,000 people, and if they're randomly selected, then you can imagine that around 50% are going to be male, 50% are going to be female. There's going to be a distribution of race, ethnicity, age that's similar to the population from which they were sampled. Now I have those individuals. I've already randomly picked them once. Now what I want to do is randomly assign them to the experimental or control groups. So I randomly assign 5,000 individuals to the experimental group and 5,000 individuals to the control group. If I do that randomly, what should happen is those two groups, the experimental and control, should look similar. So the average age should be similar. The gender, racial, ethnic distributions should be similar to one another. So what I've done is I've taken out all of those extraneous variables that are related to age, race, ethnicity, all of these participant characteristics. I've equalized them. So what should happen is when I look at the difference in blood pressure after one group gets the experimental drug and the other group gets just a sugar pill or something that isn't the experimental drug. When I look at the difference in blood pressure at the end, what I should be able to say is the drug made the difference. So let's say the blood pressure medicine brought down the average blood pressure by 10% in the experimental group. Because I've taken out all of those extraneous variables, then I can actually attribute that 10% decrease in blood pressure to the blood pressure drug, not things that are making the groups different. So if I forgot to randomize on race, and what happens if, so the experimental group is, more of them are Hispanic than the control group. What would happen is, then I didn't actually control for the difference between Hispanics and non-Hispanics in their reaction to the blood pressure medicine. So actually it might be something that's specific to Hispanics. Maybe it's cultural, maybe it's actually biological or something. So I wouldn't have controlled for that extraneous variable. And that's really why we want to use this randomization, is it just randomly distributes all individuals to make groups similar to one another before you start the experiment. I'll talk a little bit more about experimental control because a lot of that was randomization. So a control is a group that really doesn't receive that effect. So this would be the group that receives the sugar pill. If you're doing an experiment on how exercise influences depression, you'd randomly select two groups. One group would get a certain kind of exercise, so maybe 30 minutes a day of cardio, 10 minutes a day of weight training, 10 minutes a day of stretching, and that's your program for exercise. The experimental group would go through that, and you'd want to make sure that they're doing that, so you'd actually probably have them come to your lab and do that every day so you can monitor them, make sure they're adhering to your protocol. And then you'd have the other group, which would be the control group, who doesn't exercise or doesn't increase their exercise. So how you operationalize exercise makes a difference to this, because maybe you want them to exercise an additional 50 minutes to whatever they're already doing, or maybe you want to make sure the control group isn't exercising at all. So you tell the control group, you can't exercise for the next 6 weeks, and I want to see how your depression goes up. So the control group is really what you're always testing against. The experiment is what you think is making the change in the outcome, and the control is who you're comparing that to. That's really where you're setting your kind of baseline. You're making sure you're finding differences in the experimental and the control group. We'll focus a lot on experimental design and how to make it stronger than what I'm talking about now. And I think that's really important, because this kind of just very basic experimental design has a lot of issues in and of itself. I've talked a lot about independent and dependent variables already. Hopefully you read so you know what the heck I was talking about. So the independent variable is the actual cause. So this is the exercise. This is what we think makes change in the outcome. We call it an independent variable because it's independent of the individual. So if we randomize our two groups, and one group of 5,000 is taking the blood pressure medicine, the other group of 5,000 is not taking the blood pressure medicine, that blood pressure pill is independent of the individual, independent of all their characteristics, and that's why we call it an independent variable. We can also call this the explanatory variable because it explains change in the outcome. We also call it a predictor variable because it predicts change in the outcome. This is what in experiments is manipulated by the researcher. So this is the exercise program that we put people on. This is the blood pressure medicine. So this is what we're manipulating. In non-experimental research, this usually isn't manipulated by the researcher. This is something that is an individual characteristic that you think actually is important in predicting an outcome. It gets a little bit murkier when we're doing non-experimental research and how independent and dependent variables are defined. Dependent variables, we also call them response variables because you're expecting a response. So the independent variable would be the blood pressure drug. The dependent variable would actually be blood pressure. What you're measuring is the outcome. This is usually measured by the researcher. In non-experimental methods, both of them are measured by the researcher, but this is really in the context of experimental methods. So we've talked about construct validity, how well our definition of something measures that something. Now we talk about internal validity. Internal validity is very much related to experimental and non-experimental designs. Internal validity is our ability to draw causal relationships between variables. So that's why I highlighted this, is the idea of causality is really inherent in internal validity. So did the blood pressure drug reduce blood pressure? Did it cause a change in blood pressure? That would be our measure of, well, I shouldn't say that would be our measure of internal validity, but what we would say is, does the internal validity in our experiment give us the strength to say the blood pressure drug was the cause of the change in the blood pressure? Because you can imagine, even if, let's say, that blood pressure study started in bad economic times, so the housing downturn about 3 or 4 years ago. If we started the blood pressure study then and followed individuals over 2 or 3 years and the economy came back and got strong again, there's a potential that it was the change in economy that reduced individuals' blood pressure, not the blood pressure drug itself. So we'd have to consider that when we're judging the internal validity of the experiment. What are the alternative explanations to the relationship between these things? So for causality to exist, for us to be able to say X caused Y, there are some things we need to be able to do. First, we need to know that X came in time before Y. So exposure to the blood pressure drug came in time before the reduction in blood pressure. Exposure to exercise, or like exposure to the exercise program, came before change in depression. So we have to set temporal precedents. So the independent variable comes before the dependent variable. Also, we need to make sure that these two variables, the independent and dependent variables, covary together. So there actually is a relationship. As one changes, the other changes. It doesn't matter if one changes, the other decreases. As one decreases, the other increases. If there's a curvilinear relationship, we just need to make sure that they vary together in some sort of systematic way. Finally, the elimination of plausible alternative explanations. So was it the economy or was it the blood pressure drug? Being able to remove all confounding variables. So if we're able to demonstrate that X came before Y in time, that there's a strong relationship, so say there's a strong correlation between X and Y, and we're able to eliminate all confounding variables, so we've done a really good control type study, we would have strong internal validity. Internal and external validity, you can kind of think are sort of on a seesaw or on a scale. So as internal validity increases, external validity tends to decrease. So internal validity is our ability to make causal statements about relationships. External validity is how much we can generalize our results to a population. So you can imagine as internal validity increases, so we're removing all of these possible confounders. We're having people exercise in a given room with a certain temperature. They're wearing certain clothes. All of these things that could influence how exercise is related to depression. In the end, how much does that relationship really matter? Because some people are going to exercise differently. Some people are going to exercise in different clothes. And even just when we're talking about how people exercise. So some people are going to exercise really hard and get up to their VO2 max and just keep it there and go really hard. Other people are going to exercise for those 30 minutes, just kind of meandering, not really trying too hard, just waiting for the 30 minutes to be over. So that's natural, that's human variation. That's how we act, because we have personalities and we get angry and hungry and we're humans. We have variation. So when we increase the internal validity and remove confounding variables, we're kind of taking away the ability to generalize our findings. So as generalizability increases, so the more we're able to talk about our results in the context of real life, so when we measured people in their everyday, actually measured the kind of exercise people were doing themselves, taken that into account, had these different measures of depression that weren't, clinical measures, actually just really maybe subtle how people feel from day to day. What happens is our ability to make causal statements is decreased, and that becomes problematic. So field experiments try to reduce the impact of these experiments, kind of taking things out of their context, on external validity by doing them in the field. So you'd actually take your experiment, and instead of having people, maybe run inside on a treadmill, you'd go outside and just pretty much have them exercise how they normally do. And then you'd have to measure the different variables and how they do that. This example is, or the book's example, I think, was talking about like anxiety response. I actually don't recall it, so I won't use that example. But an example could be anxiety response to like eye contact. So let's say that you're really interested in how eye contact influences anxiety. So you go to you're in a lab, you have people set up on some kind of, eye contact machine, and you measure their anxiety by physiological responses of stress and heat on their skin. So that would be, you could probably find a really strong causal relationship between eye contact and anxiety. But does it matter in everyday life? When people can avert their eyes, does it matter? So what you would do is you would take that experiment to the street. So you would, have an experimenter stand there and try to stare people down on the street and see how they respond. And then maybe after they, and this is just normal people day to day walking through the streets. So what you would do is you would have your accomplice stare people down. Hopefully they don't get in any fights or anything. But then afterwards you would go and ask that person that was on the street, how did you respond? Can I maybe take a measurement of your blood pressure or your body heat and that kind of thing? So a field experiment tries to minimize that impact on external validity by doing the experiment in its natural setting. A reason that a lot of studies can't be done are going back to the ethical implications of it. So, if we're talking about a drug, so let's say a cure for cancer or something like that. So you come up with just a drug that cures all cancer. How are you going to ethically test that drug? Because you're going to have a group of 5,000 people with cancer. You give the drug. The other group of 5,000 people with cancer, you don't give the drug. Even if your drug does a very good job of reducing cancer and eliminating cancer in individuals, you're probably not going to get away with it. The IRB is going to say, well, if your drug's effective, then you need to give it to everybody because you're killing 5,000 people by not giving them this drug. So it's really hard to overcome these ethical considerations in doing these kinds of experiments. So, it's just another level of difficulty and complexity that we have to deal with as researchers. I've used this term already, participant variables. So this is characteristics of an individual. So if I was going to go do the exercise and depression study, I would be a white male, 33 years old, given level of education, family history of depression, how much I exercise, all of these things. These are characteristics of me. So these are participant variables, and these are things that usually you have to take into consideration, especially when you're doing non-experimental research, because this can really be the cause of the relationship between the two variables, not what you're interested in your XY design. So when we are choosing a method, so say we have an idea, we want to study exercise and depression. How do we want to do it? Do we want to do it in the lab? Do we want to do it in everyday life? How do we go about doing that? So it depends what you want to do. Do you want to find a causal relationship between things? Or do you want to describe a certain kind of behavior? So when we're looking at relationships between variables, we want to say X causes Y. We want to say X, is a causal determinant of an outcome Y. Where if we're just more interested in how people respond to exercise, or even depression generally, are people depressed, maybe we just want to interview people and talk to them about depression. So instead of using our "Are you depressed?" question or our 30-item scale of depression, we want to sit down and interview them and say, what does depression mean for you? Because even with 30 different items, maybe people experience depression differently and internalize those feelings of depression differently. So if we're really interested in describing this concept of depression and maybe not even operationalizing it, just seeing what exists as it does, we probably aren't too worried about causal relationships. We just want to be able to describe what's going on. So it's really important to, I guess, why would we even do these studies? Why do we want to know if X causes Y? Really, it's because we want to change something. So depression is bad. We want to reduce depression in our population. So if we find that exercise predicts depression, then we want to tell everybody that you should exercise for 30 minutes a day because you're going to be less depressed. It's hard to do that sometimes. It's hard to, if we really want to change a group. So let's say we have some severely obese individuals that we want to change their behavior because we know that their health, like their I guess, body composition at the time is a real threat to their health, and for whatever reason, this is a very important group of people. We're not too worried about if one specific method causes them to lose weight. We just want them to lose weight, so we're going to do anything we can to make that change. So when we really want to change and predict future behavior, sometimes this, like the internal validity of the design, is not so important. We just want an outcome. We just want to make change in a behavior or a state of body mass and that kind of thing. So sometimes cause and effect is really not that important. Going to kind of what I talked about over here with my structural equation model that I have already erased. Usually the best way to get at any question is to go about it multiple ways. So, I'm looking at buying a truck, so instead of just like asking the person on Craigslist, oh, is it a good truck? I'm going to get the VIN number and go on Carfax and look to see if all of these things. I'm going to call my dad, who's a truck guy, and say, is this a good year of truck? I'm going to look at all of these different things before I make a decision and say, oh, I should buy that truck or not. So this is, this applies to research methods too. And if we're interested in the relationship between exercise and depression, we probably want to do a lab study that shows a strong causal relationship between exercise and depression. But then we probably want to do a field study to see if people experimenting or people exercising in their everyday lives, just however they can, actually reduces their depression. We also maybe want to ask people, why do you think exercise reduces your depression? Why do you think exercise makes you feel less depressed? Tell me more about your kinds of exercise. Tell me more about your depression. So a more descriptive way to get at the questions. So really what you want to do is kind of go at it from all different angles. If you're only given a certain amount of time and money to ask a question, you kind of have to focus on one of the different methods. But usually when we're talking about something like exercise and depression, one person doesn't do all of the studies. So I'm not going to be the only person who's done research on exercise and depression. There's probably 100 to 200 other research scientists out there who have studied how exercise and depression are related. And they've, some of them have done descriptive studies and looked at that. Some of them have done lab studies. Some of them have done field studies. And that's really how science is built, is like ideas and topics and these relationships are not defined by one person, but we all go about doing it. And that's, I guess, going back to the start. That's why we operationalize things, is because we all need to know what we're measuring so we can all go about different ways of answering the questions and that kind of thing. So we'll talk quite a bit about validity. We'll even talk about other kinds of validity. But this is really important for us, so we'll just review it real quick. So construct validity. This is how well we operationalize our variable, how well we're able to define how we measured something. Is it a good definition of what's being measured? Internal validity. This is about causal relationships. So can we draw causal conclusions about the relationship between x and y. So that's internal validity. So you can kind of think of construct validity as its own thing. That's more of a measurement issue, so how we measure things. Where internal and external validity, these are related. So like we said, internal validity increases as we reduce all confounding variables, but that sometimes reduces the external validity because we live in a world of confounding variables. Now, external validity is about generalization, how well we're able to generalize our results to populations of interest. So everyday life, so that's kind of on a continuum of we have external validity on one side and we have internal validity on the other. So some people want to really just focus on internal validity. So if you're a physicist and you're interested in how one specific component of an atom associates with something else, you don't care how that can be generalized because it doesn't matter. It doesn't matter in everyday life. It's on such a small scale that it needs to be measured with internal validity, and that's the focus. So on the continuum, it's over here. But when we're talking about something like exercise and depression, we probably want to fall somewhere in between the two. So we want to be able to generalize our results and have an impact on people, but at the same time, we want to reduce extraneous variables. We want to make sure we're being as rigorous as possible. So internal and external validity are kind of related. You can kind of think of them on the same continuum. But I think that's it.